and all that, I'll quickly show you for your understanding what are these things actually, the low index planes and these things, because you should have the basic understanding of the crystal structure before proceeding for these things, all these discussions which are following. So in the CS1 part, you must be having all these things: crystal planes, directions in a crystal, in cubic planes, all those planes and directions in a lattice. So those are the things. Do you remember those things, or have you studied those things? Because you have to take the class on or the exam on CS1 also, for some people at least. Is it not? So I'll quickly browse you through the crystal directions and planes in crystals. Okay, so you see here in cubic unit cell. So the if this is a cube, do you understand these things? Are you able to see the screen?
Yes, sir, it's visible.
Yeah. So if that is a cube, see, all the metallic crystal lattices in general, the very basic crystal lattices are classed into basically three classes. One is body centered cubic, another is face centered cubic, another is hexagonal close packed. So other than the hexagonal close packed one, basically other two are cubic lattices. So this is one cube. So this is one cube. So what is there? If you take this point as the midpoint of this cube, then there are three directions. Like this is the x direction, this is a y direction, this is a z direction. Now, the designations of different kinds of directions and planes, that has to be understood properly so that you can understand the mechanical behavior of solids. Otherwise, you won't understand these things. So I'll quickly, yes, were you? Please mute yourself. Please mute yourself, otherwise you won't. I am hearing some sound. Have you muted, all of you?
Yes, sir.
You muted?
Yes,
yeah.
Sir.
Okay. So now, okay. See, you see here from this midpoint, this is one edge distance, one. Now, along the x direction. Now, along the y direction, after this point, you are not moving anywhere. So this is resting at this point. So this is 1, and you have not moved from this towards the y. You have not moved, and you have not moved to z direction also. So this is 1, and then 0 and 0. So this is particularly, if you notice this vector, so this is 1, 0, 0 direction in the cubic lattice. Tell me, have you understood this thing?
Yes, sir.
Yes, sir.
Okay.
Yes,
So
sir.
now, if you try to have another one, like this one is 1, you have moved one distance towards the y direction and stopped here. You have not gone any distance towards the z direction. So this is then 1, 1, and you have not moved anywhere towards the z direction. So this is 1, 1, 0. Is it okay with you?
Yes, sir. Yes, sir. Okay.
Yes, sir.
So now, if you want to have a direction which is 1, 1, 1, then you have to come through this, then come to this, and then come to that. That is 1, 1, 1. And from the origin, you have to draw one line like this, so that this particular line indicates the 1, 1, 1 direction. Is it clear?
Yes, sir. Yes, sir.
Okay. So likewise, in any book, because you will be studying this, CS1 part, the crystal structures, directions, the atomic packing factor calculations, and all that. Professor Dr. H.S. Tripathi definitely is taking these classes and all. So if you want me to share with you these things which I teach in my class, it's okay. I'll send you. Otherwise, these things you study very carefully, otherwise you won't understand what I'll be teaching now. So now these are some planes and directions. So these are midway the calculations. Now for the plane, this was for the direction. Now this is for the plane. What is for a plane? So this is again from the midpoint 0, that is the origin. You moved a distance 1. You have moved a distance 1. Now from the origin again, you are not moving anywhere. So this has touched upon this point. So if you go through this plane of this cube, this edge of the cube, which is in the front part of you, that is, you can see this face of the cube. So this direction, this plane is 1, then 0 and 0, because if you want to have the intercepts, then you have to take the reciprocals. That means 1 by 1, 0 by 0, and then 0 by 0. What does it mean? That is, the intercept along this axis is 1, intercept along the y-axis is infinity. 0 by 0 is infinity, and intercept along the z-axis also infinity. What does it mean? That means that plane is not touching your y-axis, is not touching your z-axis. That means that particular plane 100 is only having an intercept in the x-axis to the tune of 1 unit length, but that plane is actually parallel to the y-axis and parallel to the z-axis. That's why it is 100 plane. Is it okay?
Okay.
Yes, sir. Continue.
Okay, sir. Okay.
Then next, you see here, you have moved one distance here. That is 1. You have moved one distance here. That is another 1. And then you have not moved any distance here. That means this is 0. Because you are always to take the intercept. That is 1 by 1. That is again 1 by 1. And that is 0 by 0. So if it is 0 by 0, that is infinity. That means it is touching the x-axis at one distance, touching the y-axis at one distance, but it is actually parallel to this z-axis. That means it is not someone is coming. I am admitting him. So let me just wait for him to, yeah. So why are you so late, Prithvi Chandrasekhar? See, the class was to start from 7 p.m. I have already started after waiting for 10 minutes and joining at 7:20. So in between, if I had to disrupt the class, it's pretty difficult.
Sorry, sir. Just I came to room, sir.
Okay, it's okay.
From office.
You are, yeah, okay, understandable. Okay, now see.
Okay, sir.
So this is having one intercept 1. This is having another intercept 1. That means it's cutting the x-axis at 1, y-axis at 1, but it's the plane, the shaded region is actually cutting the x-axis at one distance, cutting the y-axis at one distance, but it is not cutting the z-axis with anything. That means it is parallel to the z-axis actually. So this is a 110 plane. See the next one? See, it is cutting the x-axis at 1, cutting the y-axis at 1, and cutting the z-axis at 1. And you just draw the final points. So that the diagonal plane of that cube, which is the shaded one, is the 111 plane. So this is very vital. You must know this thing. This 110 plane and 111 plane is very, very vital in some of the mechanical behavior, explaining some of the mechanical behavior. That's why I am explaining this thing. Otherwise, I could have just passed to the main discussion of my part. But because it will be difficult for you to understand if you don't have this basic understanding, I am repeating this thing. Okay? So, This is 100 plane, this is 110 plane, this is 111 plane. See, in the materials which you talk about, suppose iron, FCC iron crystal structure is face-centered cubic crystal structure. Definitely, in some of the other modifications, it may not be FCC also. It is something else. But cubic structure, it's not a hexagonal structure. But when it's a cubic structure, in the iron lattice, if you go to the atomic planes and directions, these are like this. Because in FCC, there are 111 planes, there are 110 directions. 110 direction I have already shown you. 1 direction, have I not shown you? Have I shown you the 111 direction? One direction. Why 110 direction? 1, 1, and then you don't move. So this direction is 110. This direction is 111. 1, 1, and 1. So this is 111. Okay? Is it clear now?
Yes, sir, clear.
Okay. So this is 100 direction. This is 110 direction, like that. Okay. Now the planes, 100 plane, 110 plane, 111 plane, like that. So there are like this many things. This is a 632 plane. So this is a 101 plane because this is 1. Then you don't move somewhere, and this is 1. So 1, 0, 1. So these are the final points, and you draw this plane. So this is 101 plane. This is 1, this is 1, and this is, you don't move anywhere. So this is 110 plane. Okay, so these are the things. Now, let me come to the main points where I'll have some glimpse of those things. Now, you see, we will be discussing plastic deformation. Means, you are having, suppose, an iron bar. Suppose a rectangular iron bar or squarish type of iron bar. This is a cube type of iron bar. Now, or a rectangular type of iron bar, or whatever, a cylindrical iron bar, or something like that. You clip it at the ends, and then you try to move apart. That means you are pulling it apart. So what will happen? Inside, there will be some changes in the atomic structure. How it will be affected? Because any material, any solid material, they are consisting of this type of crystal structures. Like they may be having a cubic crystal structure, or maybe hexagonal cubic pack, close pack, or some others. But most commonly, cubic structure or hexagonal close pack structure. Now, amongst the cubic structure, either they are body-centered cubic or face-centered cubic. Do you understand what is body-centered cubic and face-centered cubic? Tell me frankly.
Yes, sir.
Yes, sir.
Everybody knows?
Yes, sir.
In the center of body, it is
Yes.
body center.
Center of body and center of faces.
It is.
Okay. So all those are lattice points. All those are lattice points of the cubic unit cell. For a body-centered cubic lattice, what is the number of atoms per unit cell? Can anyone tell me? What is the number of atoms per unit cell for a body-centered cubic lattice? These things were discussed in my last class. Just I am asking randomly. For a body-centered cubic cell, what is the
There are
number of atoms per
atoms.
unit cell?
2 atoms per unit cell.
Yes, 2 atoms per unit cell. For FCC, it is 4 atoms per
4
unit
atoms.
cell.
4 atoms.
Yes. Okay. So now, try to understand the thing. Suppose this type of cubic unit cell is there. Now, that may be either a face-centered cubic cell or a body-centered cubic cell, or a hexagonal close-packed cell. So now we are to know the atomic density of the low index planes. I have shown you some planes, like 111 plane I have shown you. I have shown you 110 plane. There are hazar planes. There are hazar planes. You can have the planes designations. Those are Miller indices actually. This 110, 111, 100. So these are all Miller indices of the planes. And now Miller indices can be derived from the intercepts, taking the reciprocals, and then finding the LCM, you can have the Miller indices of the planes. Now you know this face-centered cubic, body-centered cubic, and hexagonal close-packed. Suppose for the octahedral plane, I have shown you the octahedral plane, that is the 111 plane, the name is octahedral plane. Now, what is the atomic density? That means the atoms per unit area is 4 by root 3 A0 square, where A0 is the lattice distance. Now, 4 by root 3 A0 square is the atomic density. That means atoms per unit area. इतना एरिया में कितने नंबर ऑफ एटम्स रह सकता है, दैट इज द एटॉमिक डेंसिटी, दैट इज द एटम्स पर यूनिट एरिया. नाउ टेल मी वन थिंग, आई एम आस्किंग यू वन ट्रिकी क्वेश्चन. You place some marbles on the floor, each marble touching each other, and in another set you place the marbles 1 and 2 touching each other, then at some distance 3, 4, 5 touching each other, then at some distance 4, 6, then at some distance 7, 8, 9, 10 touching each other. In the first instance, all 10 marbles are touching each other. In the second instance, as I told you, 1, then 2, 3 together, then 4, 5, 6 together, then 7, 8, 9, 10 together. But these sets are not touching each other. Now, you start from the first instance and from the second instance, you start pushing the marble from one end. You have started pushing the marble from one end, in which case the marbles are touching each other. And in the second instance, you have started pushing the marble from one end, wherein the marbles 1 and 2 touch each other, at a distance 3, 4, 5 exist, at a distance 4, 5, 6 exist, and 7, 8, 9, 10 at a distance. And you have started pushing from the marble from the end of number one marble. Now tell me, any one of you, in which case I would require less amount of stress. That means my pushing, what, in which case I would require less pushing for the 10th marble to move. Can anyone tell me?
For the first case, sir.
For the first case,
It requires less stress to move.
very good. Who told you? Who told?
Ajay.
Ajay. Very good. Because why this is so? Because this inner distance, the atomic density is more. That means which is close packed. That means तुम अगर 10 सेंटीमीटर लगाए हो डिस्टेंस, इन दैट 10 सेंटीमीटर 10 मार्बल अगर रह गया, दैट मीन्स दैट इज क्लोज पैक्ड. एंड इन दैट 10 सेंटीमीटर, in the second case, there are not 10 marbles. That means it is loosely packed. So which is the close packed one? You need less amount of stress to move the 10th marble. That means the deformation, if you want to have some effect on the behavior of stress on a material, then the material which is close packed one, that would be affected first. That means that is easily deformable. Is it understandable?
Yeah, yes, sir.
Clear?
Yes, sir.
एकदम क्लियर. दैट मीन्स जो एकदम कॉम्पैक्ट है उसमें लेस एफर्ट से आप उसमें डिफॉर्मेशन करा सकते हैं. दैट मीन्स in a solid material also, in a metallic material, the material, that means the structure which is very compact in nature, that means whose atomic density in that plane is very high, that means which is closely packed, that means whose packing densities are high, they are affected first. That means if you apply an X amount of load, then that X amount can affect the highest packed plane first. Not the loosely packed ones would get affected by the application of X amount of stress. They will get affected, but later on, as you apply more and more stress, one by one, those loose packed planes will get affected, but not the compact ones. Compact ones will get deformed first. Deformation means when you apply a stress, I am getting a strain. So that is the deformation. Strain means length per original length, change of length per original length. And the stress is application of stress. And the stress is proportional to strain in the initial period till it is recoverable deformation. That means if you plot a stress-strain curve, then in the initial part, when suppose you are having one rubber band with your hand, rubber band, you cut it and then you hold it with your hands at the two ends and you stretch it. As you stretch it, it becomes longer and then you release it. It comes back to the original position. And you again stretch it, it becomes longer, it comes back to the original position as you relax the stress. If you start doing it indefinitely, if you stretch it beyond a certain limit, then it becomes stretched and does not come back to the original position. That means if the original length was something like 2 inches, then that 2 inches become 2.2 inches after you have applied so many stressing. Do you understand that thing? In the first instance, that means when you have stretched to certain extent that it remains as it is recoverable deformation. That means stress is proportional to stress to the limit at which when you relax the stress, it comes back to the original length. But as you cross that particular point or point of application of that stress, if you increase that stress further, then for a deformable material, so there comes the distinction between a metal and a ceramic material. For a ceramic material, this does not hold good. ये ceramic material के लिए नहीं है, ये metallic material के लिए है. क्योंकि आप metallic material पे आप hammer करोगे, कुछ उसको ऐसे खींचोगे, तो metal deformation होगा. लेकिन ceramics क्या होगा? Refractory break हो जाएगा. Deformation नहीं होगा. Deformation? Have you seen any material, ceramic material to get deformed? ऐसा hammering करोगे?
No, sir.
नहीं होगा. So in ceramic there will be brittleness, but in metal it is ductile. So there remains the difference between a ceramic and a metallic material. That a metallic material is a ductile material, a ceramic material is a brittle material. A brittle material is a material in which if it is not having any plastic deformation, which is written here in the top. So ceramic materials are not plastically deformable, whereas all metallic materials are deformable, but it depends to the extent at which the deformation takes place. The maximum deformation takes place to the maximum close packed lattice, as I told you just with the example of marble, that the material which is maximum compact, the deformation would be maximum for that. So that means that material is very, very plastic and very, very ductile. So face-centered cubic lattice here, you see the octahedral plane 111 is having the maximum atomic density. That means when you apply a stress, the octahedral plane would be affected first. उसमें ही सबसे ज़्यादा इफेक्ट होगा. And interestingly, these planes are also the most distant planes. एक plane से और एक plane का distance, though it is in atomic distance, in some angstrom units. Just think of the material's atomic entities. It is inside the material. I can't see this, but this is there. And that's why in a macro scene, you are experiencing this kind of behavior from a material. Can you understand this thing? Visualize this thing, that this is happening inside a material. That there are so many planes, you are applying a stress, but first of all, the octahedral plane gets affected, and this is the most distant plane. One plane is situated at a distance from this one, and plastic deformation takes place. So face-centered cubic lattice, for the octahedral plane, the atomic density is maximum. For the body-centered cubic lattice, the dodecahedral plane, 2 by root 2 A0 square, this is the highest density plane. So this, like this 110, there are 112, 123, different types of planes are there in BCC. Not a single plane, but there are different kinds of planes which are of similar atomic density, but not as compared to FCC. So BCC lattices are not as plastic or as ductile as the FCC metal. BCC metal are less ductile. Hexagonal close packed are in that sense not at all ductile like FCC and BCC, because they are only basal plane. See, this ductility also depends on other factors also. So how many of these planes are there? How many directions are there in which those planes would move? So planes into directions that give you the number of slip system in a particular crystal structure. So in case of FCC, that is the maximum. So slip system, and that slip system is the maximum effective one for having the plastic deformation tendency for that material. So from this chart, I will move to the plastic deformation. You see here, it is written, plastic deformation is generally confined to the low index planes, higher density of atoms per unit area than the high index planes. List the atomic density per unit area for the common low index planes. Planes against greatest atomic density also are the most widely spaced planes for the crystal structure. Understandable? Now you see, deformation by slip. I'll show you some figure and then make you understand what is that. See, in the material, in the atomistic level, what is happening? See, there are these crystal planes. Suppose here the arrangement is like this. This is separated by an imaginary slip plane. So that slip plane, along these planes, if you apply, suppose a shear stress in the crystal, with the crystal. So this is moving along this is moving along this. So first arrangement was like this, the atomic arrangement. And the next part, because you have applied the shear stress, these planes have moved two distances along this direction with respect to this plane. That means, if you observe under the microscope, you will see this line, only this line, because you can't see this, you can't see the atoms, but you only notice this line. But inside the material, what has happened by then, after the application of shear stress, after a certain time, that these plane of atoms have moved two distances with respect to these plane of atoms along this line. So under the microscope, you will be seeing this line. If you polish the surface, it will be like this. Then you cannot notice this thing. But inside the material, this has happened, that these atoms have moved. Do you understand this thing? Can you visualize what is happening inside the material? So this is called slip deformation. And when you are applying a stress to a metallic crystal, suppose an iron bar, actually inside the crystal this is happening. You cannot notice it with your naked eye, but this is happening inside the crystal. And these slip lines are like this. If you observe under the microscope, this will appear like this. If you polish the surface, you won't notice anything. So this particular thing is being depicted here. Okay, so you study this thing. So these are fine structure of a slip band, small deformation, large deformation like this, and slip planes and directions. These questions are asked in your question paper. In many years, I have set the questions. I have asked you to answer like this. Amongst BCC, FCC and HCP, or what are the slip systems or slip planes and directions in case of BCC, FCC and HCP? You see here, it is clearly written here that in the hexagonal closed pack, see, slip plane together with the slip direction establishes the slip system. Now it is written here. In a hexagonal closed pack metal, only slip plane with high atomic density is the basal plane. Basal plane is the 0001 because the hexagonal closed pack lattice is a different one, not HKL indices, this HKIL indices, because 3 120 degree direction at the basal plane and then 1 C direction, that is HKIL indices is said, and the axis 1120 the closed pack direction. So there are zinc, cadmium, magnesium, cobalt slip occurs on the 001 plane and then 112/0 direction. Since there is only one basal plane per unit cell and 3 directions, HCP structure possesses only 3 slip systems. The limited number of slip systems is reason for the extreme orientation dependence and low ductility in HCP metals. So you find the explanation of low ductility or low plasticity for HCP. Is it okay? In the next case, face-centered cubic lattice, you see the 111 octahedral plane. I have already shown you the 111 octahedral plane. Have I shown you? Have I not shown you? Yes? 111 octahedral plane. I have shown you now?
Yes, sir.
This is 111 octahedral plane.
Yes, sir, already, sir.
Yeah.
Okay. So 111 octahedral plane and 110 direction, that also I have shown you, are the closed pack systems. So this is the closed pack systems. Now 8 111 plane are there. They are at opposite face. So 4 sets. And each 111 contains 3 110 direction. So 4 into 3, reverse directions being neglected, 12 possible slip systems are there. So number of slip systems is more. As well, the atomic density are more. So FCC has got the maximum low index planes and maximum number of slip systems. So FCC is the most ductile and most plastic material. And another thing you see here, the BCC structure is not closed packed like FCC or HCP. Accordingly, there is no one plane. See, this is BCC structure HCP की तरह closed pack नहीं है. इधर हम closed packness के ये बात नहीं बता रहे हैं. We are talking about slip system. BCC में slip system ज़्यादा है, लेकिन BCC closed packed नहीं है. HCP is a closed packed structure in that sense. But because HCP has got less number of slip system, that's why HCP is not ductile. Because for the ductility or plasticity to take place, if you apply a stress, that stress had to relax along those planes and move along those directions to take the deformation forward. In HCP, because the number of slip system is less, So HCP is not as plastic as FCC or BCC, even though HCP is more close packed than BCC. But because slip system is less, so the slips cannot move along the slip planes and directions. That's why HCP is less plastic in that sense. So you see here, there is no one plane of predominant atomic density like 111 or 0001. इसमें है ही नहीं. कौन सा है? 110 है थोड़ा सा, 112 है, 123 है, ये सब कंपेरेबल एटॉमिक डेंसिटी का है, लेकिन एफसीसी की तरह नहीं है, एचसीपी की तरह भी नहीं है. लेकिन नंबर ऑफ प्लेन्स 110, 111, 112, इसका 123, ये सब प्लेन थोड़ा सा है जिसमें स्लिप हो सकता है. And they all contain 111 direction, and that is close packed as 110 and 112/0 direction. That is okay. That is 111 direction. That is close packed. But because slip planes are not as close packed as those ones, BCC is not as ductile as FCC. And HCP is not as ductile as BCC because HCP has got less number of slip systems. So these particular portions discusses your explanation as to why the materials HCP, FCC and BCC are responsive to application of stresses, and why FCC is most plastic, why BCC is intermediate and HCP is not ductile at all in respect of slip planes and directions. Okay? Now, slip in a perfect lattice. See, I have another 10 minutes because you have the maths class, is it not? Now tell me, how are you enjoying this thing? Is it understandable what I am saying?
Yes, sir, understandable.
Is it okay, understandable?
Yes,
everything
sir.
Being crystal clear now?
Yes, sir, crystal
so
clear,
I have
sir.
supplied you all these study materials. If you go through it after I have deliberated, after I have explained you everything, if you study those things which I have given, then I think you'll be very able to understand and will be able to answer my questions also. Okay? So now let me again come to this for 10 minutes more for sleep in a perfect lattice. So this is often asked in the question paper. Sleep in a perfect lattice means, suppose this arrangement was like this atom was initially above this. After you have applied a shear stress, this particular thing has moved like this. So it has become like this. And the stress distribution is like this. So this one is tallying to this. This 2 is tallying to this. In between the 1. Now what happens? If you apply the stress along this direction, there is a displacement. That means this displacement means when you are applying the shear stress, the plane of atoms are trying to move from one side to another. So this is with respect to this plane, this atomic planes is moving towards right. Now the stress distribution is like this. So when the 1 was here, there was 0 displacement. When 1 is in between these two, this is again 0. When 1 is coming over 2, this is again 0. But in between, this is having a maxima at the midpoint here, and it is having a maxima at the midpoint here. How does it happen? Now, this 1 was originally here. Now, as you apply the stress, this 1 is trying to go towards the right. As it tries to go towards the right, in the initial part of this curve, it is recoverable deformation. That means there is no displacement. Like if you, before the midpoint of these 2 points, if you relax this thing, it comes back to original. But if you cross the midpoint of these 2 points, this and this, then it reaches here. As it reaches the midpoint and it crosses, it comes here. Then particular ball, it is going towards, again coming through a maxima and then falling to a minimum. So it passes through a maxima, passes through a negative maxima here and coming to this thing. So this distance of this point to this point is one interatomic distance B, and this is the interplanar distance is A, and this is the displacement X. Now there is a simple mathematics. The first approximation, this curve, sinusoidal curve, is well represented by tau equal to, tau is the stress, tau m is the stress maximum, sine 2 pi x by b. X is this, and b is this. So x by b is the strain. That means x by b is the strain. So tau m is the amplitude of sine wave, b is the period. At small value of displacement, I told you, Hooke's law should apply. So stress is proportional to strain. So tau is proportional to gamma. That is, tau is equal to G into gamma. G is the shear stress, and that is equal to, gamma is already I have told you, that is x by A. So that is, sorry, x by not x by B, x by A. So angular strain. So tau equal to G gamma, that is Gx by A. Now for small values of x by B, that can be written, because sine something, sine 2 theta, when theta value is very small, for a simple trigonometry, sine 2 theta is simply 2 theta. Do you remember those mathematics? So for this equation, tau equal to tau m sine twice pi x by b, for very small values of x by b, so this becomes tau equal to tau m twice pi x b, because this is twice pi is only twice pi. So twice pi x by b. Clear? Is it clear?
Okay, sir.
Okay. So combining these 2 equations now, tau m equal to G by 2 pi into B by A. You might have noticed this question was asked in previous years also, where you had to deduce slip in a perfect lattice. So that from tau m equal to G by 2 pi into B by A. So this B can be equal to A for cubic lattice, interplanar distance, and interatomic distance may be similar. In some situation, A may be equal to B. So for that thing, for a perfect crystals, shear strength of a perfect crystals is approximately equal to shear modulus, that is G by 2 pi. That is, when B equal to A, tau m becomes G by 2 pi. Now G is value is varying from 20 to 150 gigapascal. So tau m equal to 3 to 30 gigapascal. I think I rest here because there is another class of Professor Mahmood. So he will be waiting for you. So we'll discuss in the next classes. Okay?